discussing the solution of assignment number 7. So the questions are as follows. So in first question they've asked us to estimate the transverse modulus of glass epoxy composite with a volume fraction of 0.25. So this is the formula which is true for calculating transverse modulus. That is, it gives more accurate results, as sir has already explained in his lectures. So putting these values into this formula, we have Et by Em is 1 plus this formula. For eta, we use this particular equation. So we have Ef by Em. That is the Young's modulus of fiber is to epoxy as 70 is to 3.5. So 70 divided by 3.5 gives a value of 20. So 20 minus 1 is 19 and 20 plus 2 is 22. This epsilon value is 2 because in case of circular cross sections A and B, that is the dimensions of the fiber cross section are same. That's why A by B would be 1 and epsilon value would directly be taken as 2. So once we put this uh, into this formula, just so once we put this into this formula, we get the value of Et by Em to be 1.86. We multiply it by Em and we get Et to be 6.39, which is close to the third option, that is 6.5. So now moving to the next question. Uh, It is asked that transverse modulus of unidirectional composite material is strongly influenced by which of the following properties. So this is a composite. We have fibers in this particular orientation. When stresses are applied along direction of fibers, then they are known as longitudinal stresses. But if we apply them perpendicular to the direction of the fibers, then it is known as transverse stresses. So in case of A, B and C, it is illustrated that a composite will behave like this. That is, it will expand in this particular direction when longitudinal force, that is sigma 11, is applied along the direction of fibers. If we apply transverse force, that is perpendicular to the fiber direction, as sigma 22, then this would be the cross section. Now if we see the failure mechanism of composite under longitudinal as well as transverse loads, then we can see that in case of longitudinal directions, fiber breakage occurs followed by debonding at the fiber matrix interface or matrix cracking or multiple fiber breakage. But in case of transverse modulus, mainly matrix cracking or fiber and matrix interface cracking occurs. That is, failure mainly occurs at the matrix level, and therefore matrix properties would be the one which will be affecting our failure in case of transverse load applications. The next question, they've asked that which of the following is true for unidirectional composites when it is loaded under tension. So transverse strength is being compared. So as I've already explained in the previous slide, when we apply transverse load, that is in the direction perpendicular to the fiber orientation, then matrix is the medium which will mainly fail. So for this, we use finite element analysis to see that what would be the direction of load and the stress concentration factors. So this sir has already explained that at fiber matrix interfaces, the stress concentrations would be higher and the tensile strength of this particular composite would be governed by this particular formula. The stress concentration factor would be determined by finite element analysis or some other analytical methods. So from this formula itself, we can see that stress concentration factor would be greater than 1 and the matrix strength is given by sigma mu. So this transverse strength would obviously be less than the transverse strength of our matrix medium. So moving to the next question, they've asked to estimate the shear modulus of graphite epoxy composite. So the shear modulus is again estimated by Hafen-Tsai model, as this gives more accurate results. This is the formula. We put the values of, in this the only change is that for estimating the transverse modulus, we have epsilon to be 2 times of A by B. A by B is the dimension of the fiber. But in case of shear modulus, the value of epsilon is directly 1. So once we put this into this particular equation, it is solved as follows, and we can see GLT value comes out to be 3.29. So which is close to the first option, therefore first is the right answer. The next question, they have asked us to estimate the major Poisson's ratio using micromechanics approach. So this is the formula to calculate the major Poisson's ratio of a composite if the Poisson's ratio of fiber and matrices are known. This is direct formula. You substitute the values and we get the Poisson's ratio value to be 0.305, which is the third option. So in the next question, they've asked that in general composites, if the volume fraction is less than 40%, then the failure mainly is seen in case of fiber breakage, but in rest cases, matrix delamination or like failures related to matrices are seen. So why is it so? So for this, we'll see that what is the stress distribution in a composite. So sir has already derived this formula in his lectures that stress in a composite is beared by fiber and the resin component, and the stress in fibers and the resin are dependent on the volume fraction of these particular materials. So we can see this is the like if we try to like further solve this particular formula, then this stress can be converted as the Young's modulus of the material into the strain, as the Young's modulus is strain divided stress divided by strain. So we like simplify this formula, we substitute these stress values in this particular equation. So this equation will turn out as follows. So this sigma c would be the stress at which the composite would be breaking, and if we divide it by the strain values, as strain would be same in case of fiber as well as composite materials, so we can see that percentages wise the fiber stress bearing capacity is increasing quite heavily as we increase the volume fraction from 0.3, 0.5 to zero point 0.7, while the matrix load bearing capacity more or less remains the same. It is 2.5, then 1.75, and then 1. So when we increase the volume fractions, the fiber load bearing capacity increases significantly, and thus the failure strength of this particular composite would be far higher as compared to that of the one which is manufactured with 0.3 volume fractions. So the load on matrix right at failure would be higher in this particular examples, because strain for this particular volume fraction would be like strain in the matrix would be equivalent to the strain which is there in this particular matrix, same as the strain which is there in fiber. So in this particular case, fiber are bearing 49 equivalent of stress. So 49 divided by no 49 divided by the Young's modulus will give the strain value at in this particular case, while 35 divided by Young's modulus, which is a constant quantity, will give the strain in the matrix in case 2, while 21 divided by the Young's modulus, that is 70, will give strain in this particular case. We can see that strain in each particular case is different because we are dividing 21 by 70, 35 by 70, and 49 by 70 in each of these cases. So strain is increasing. Now matrix will fail more rigorously when strain is higher, because the Young's modulus of matrix is quite low, and therefore for higher volume fraction cases the matrix will fail instantly, while in lower volume fraction cases the strain is lower, so that's why matrix have ample of time to expand, get some energy into itself, and then break whenever its break strength occurs. And therefore in lower volume fraction cases, fiber will be the first point of failures and matrix will still bear some load. So fiber breakage would be the point at which the failure would be seen. But in rest of the cases, fiber will continue to bear the load, but the matrix will instantly fail because the strain limits are very high. And this explains that the answer would be first, that is In lower volume fraction cases, fiber breakage will occur, while in higher volume fraction cases, matrix breakage will occur. The simple reason is in higher volume fraction cases, the strain in the composite is very high, so matrix will tend to fail early. So the next question they've asked that when the composites are subjected to longitudinal compressive modes, then which of the following failure mode can occur? So this has been taken by literature. When this is the longitudinal direction, that is the direction of fiber orientation. We apply compressive stresses. Then in first case we can see the fibers are buckling. In second case we can see there is some fiber clinking. That is it's shifting from its position. In third case, we can see matrix like fiber is crushing, matrix is in all these cases, the main observation would be that matrix is getting displaced, after which fiber is changing its shape in one form or the other. So at none of these cases we see that fiber is breaking. In all these cases, matrix is the first thing which is getting deformed, and therefore fiber breakage is the only thing which will not occur. Rest all things will occur, and therefore second is the answer. In the next question, it is asked that which of the following is common type of failure when unidirectional composite is subjected to transverse load. So this is similar to the second question. We have seen that when we apply transverse load, all the stress concentration is there in the interface region, and matrix is the major point of failure, and therefore first is the right answer. So in the next question, they have asked that for unidirectional composite, moisture expansion coefficient is virtually negligible in which of the following cases? So moisture expansion mainly occurs only in case of resins, that is the matrix medium. The fibers are quite stiff and chemically resistant, so they won't actually absorb moisture. They'll remain as it is, while the matrix will expand noticeably. So if it's pure matrix, then significant amount of expansion is seen as soon as water enters into its matrix, lattices, and the resin expands. But when the composite is subjected to longitudinal direction, then when the composite is subjected to a lot of moisture, the resin will try to absorb moisture and expand. So this expansion will induce strains in the matrix medium. The same amount of strains are getting transferred to the fiber medium. So these strains are trying to induce stresses in the fiber medium. The entire composite will only expand if these fibers are also getting deformed in the expansion, which is equivalent to the expansion caused by this particular water. So the simple reason why no expansion is seen in longitudinal direction is that the fiber has a lot of modulus. That's Young's modulus is higher along longitudinal direction, and therefore the fiber will not strain as much as the matrix, and therefore composite volume will more or less remain the same, and therefore no expansion would be seen. Now in the 10th question, they've asked us to estimate the uh, coefficient of thermal expansion. So this is all here. This is the simple formula which is used for estimating the coefficient of thermal expansion along longitudinal direction and transverse direction in case of composites. So this is the formula. We first need to calculate the modulus along longitudinal direction of the composite using this particular equation. That is the Young's modulus of fiber into volume fraction of fiber plus Young's modulus of resin into volume fraction of resin. And we also substitute the remaining values as the expansion coefficient of fiber material into the Young's modulus of fiber into volume fraction, and this is about matrix. So with this we get the value of 1.093, which is same as second option. So second is the right answer. Fine. So that was all for assignment number 6. Any one of you have some other doubts? Arun? Okay. Yes. No, MF upon MC would not be equal to zero point 0.4. The volume of fiber divided by the volume of the entire composite, that would be equivalent to zero point 0.4. Yeah, yes. Now see, if you see his lectures, it was there in last class, right? Failure mode of this one, 39. 39. It's towards the end, right? This one? Yeah, see, fibers break and pull out. So, pull out means the interface between matrix and fibers is breaking, right? Pull out means this interfacial thing, this adhesion, which is shown in this particular like figure. You can see for fiber to pull out, this like boundary of this fiber needs to leave the matrix medium completely. Only then will it pull out. So that's why 40 to 65% have like comprise of matrix along with fiber failure. But for less than 40%, it's only fiber failure. That is in this case. It's similar to this case. Okay then. Thank you then. I'm ending this meeting. We'll meet on next Monday. Thank you.